It's okay. Okay. Now it is
I'm done.
okay. Now it is also in the box is there.
Now it has come. Okay, now it has come. Okay.
Okay.
Okay, it is good. Now it has come. Okay.
All right. Great. Thanks for pointing that out. I'm here to talk about a specific concept in reinforcement learning, as you all know, called TD learning, or abbreviated as temporal difference learning. And as boring or as geeky it may sound, trust me, by the end of this session, I think you'll get familiarized with the tip of the iceberg at least. So certainly I'm going to talk about that in a bit, but I also want you to know, as people entering the field, you should be aware of the nuances, the tips and tricks that people in the industry know. On what I think it from a long-term perspective. And so this is a really special time, and we can look forward to doing amazing things, which is maybe understanding the way mind works, the way intelligence works. This is like a monumental event, not just for this decade or century, but for thousands of years, maybe in the history of Earth, when intelligent beings, animals, and things that can replicate themselves finally come to understand the way they work. And just the fact of our understanding it is going to change the world. Obviously, there will be lots of applications, but it'll change ourselves, our view of ourselves, what we do, what we play with, what we work at, almost like everything. It's a big event, and we should keep that in mind. I'm not saying that it's going to happen tomorrow or like in 2 years, but 10 years, 30 years down the line, it's surely inevitable, and that would be the great sweep of history. Uh, Coming to my third slide, there's a small amount of time, it's gonna happen within our lives with high probability. So the first thing that we have to ask is, why is this happening? Any guesses? I think it really comes down to Moore's law, the decreasing computation per cost. And it's just reaching a point where it starts to compete with the computation that we can do with our brains with natural systems. It's happening now, and it's just going to continue increasing dramatically. I'm sure you're used to seeing or presenting these kinds of slides in your routine lectures, and you see it's a log scale already. And some experts even argue that it's actually slightly super exponential with the pace that it has picked up in the recent years. With all the GPUs coming in after 2015, 2016, all the tech giants, Amazon, Google, pitching in NVIDIA, pitching in resources for that. It's the law of 7 years has become quite more super exponential. But the point is, the computations becoming available to us have become enormous, and that changes things. It's the rise of deep learning, and all that is purely because the GPU in compute is getting cheaper day by day. And that will only continue, and it will become more extreme. It really is profound, and I was just trying to say is, a few of my slides will revolve around the future prospects, and it's just there to familiarize you with the things that are happening in the industry and the ones that are there and the ones that are yet to come. And the other half then is to not forget the really small things, the fundamentals, where you go back to the foundation, the real stuff. That's basic, that we need to get along in this field. We heard a lot of specific algorithms in a lot of research that has happened in the past and how they work. It's really important the details matter, but the big picture matters too. And sometimes we lose sight of the big picture. Sometimes something becomes so obvious that we overlook it. The chess game that we used to see in 2000s happened to be a very narrow, a very specific purpose artificial intelligence that was built. While the one on right, the general AI, is the HAL 2000, which is even much more broader in those sense. And that's by scale computation. I mean, as we get more compute power, those methods become more powerful. And this has not always been tried true. But certainly it's true of learning and search methods. These are what we call general purpose methods. It's the answer to this one of the oldest questions in AI. Do we want weak methods that evolve, or do we want specialized ones that don't? It's silly that they used to call general purpose methods weak, because they use all the data, all the computation, yet they are called weak. The strong ones were the ones that would lose human knowledge and human expertise and human insight to make their systems so much better. Now, bro, you guys probably would be thinking that it's crazy. Like, how do you want a targeted, specific AI built for one particular application? How does that have an edge over? How does that have an edge below the other one that is more generic? So today I'm gonna try to put it in all this talk. I'm gonna present strong views. Really, maybe you should do compromises and nuances, but it's good to talk about strong views because they give you a working hypothesis to give you a point of view, and you can always argue that this is a strong one, and you don't want to or you don't have to believe it. Next thing to say is that you're thinking you're good, you're thinking you're into, well, deep learning or reinforcement learning, so you're on the right side of the history, but I'm not sure that it's right, because we take things like any kind of supervised learning, even model based reinforcing, the thing I love more than anything right now, it's only weakly scalable. If I had, a million times its computation, I'm still limited in my model for reinforcement about how fast I can gather data and how, and I'm only learning value function or maybe a policy. What's the big deal? Uh, any machine learning engineers or machine learning scientists, researchers in the house might agree with me that you have to craft multiple features for supervised learning. Must be in the orders of hundreds of thousands. And yet they are very weakly scalable. Uh, any guesses on why that is really weakly scalable? That is because it requires people to provide data sets, and there they become the bottleneck. If you get to, if you have to get to people to label things on the web, things scale, but only weakly, only as fast as you can gather the data, and unless eventually that becomes, the people in themselves become a bottleneck, you really won't be able to learn from that. What you want is, you want to learn from the raw data. You want to be scalable. So if these things that we love are not scalable, what is then? What do you turn to? Well, my answer to that is simple. It's what I call prediction learning. Prediction learning means learning to predict, and that will happen. Okay, so it's the unsupervised supervised learning. We've all taught, we have, in the very first three pages of any book that we receive, we've seen the three categories into which machine learning has been categorized: supervised, unsupervised, and reinforcement learning. Prediction learning is a special concept in reinforcement that I like to call as unsupervised supervised learning, because the reason is we have targets here, but they are not human specified. We just have to wait and we see what does happen, and that is what is our target. So you don't need human labeling in this. Though you need to have a target, but you don't need a human to provide it. Just get it from the data your agent observes. Anyway, it's also definitely the scalable model free learning, and as prediction learning is at the heart of all our control methods where you learn value functions, I think maybe that's the sort of argument I wanted about temporal difference. And of course, I haven't given you even the step towards that yet, but I'm saying the idea of predicting, having learning that predicts, is the key problem. That is what we should be thinking about. And you may as well say deep learning, supervised learning is all about prediction learning too, Siddharth. But that's not true. It's all about predicting what the label will be. But it's not about predicting over time. It's not about predicting where you have to wait and see what happens next. And that is what makes all the difference. So with all these words, I want to ground us a little bit, remind us what the data looks like. I've put in a slide of this, what real life is like. Real life is temporal stream. We have things like playing soccer and we have to make actions at every moment. We are maybe a mongoose in the right side image being chased by a lion and trying to predict whether I'm going to live or die. Or contrarily, how the chase looks like to the lion, whether I'll be able to have my food for the day or not. We are maybe even a cricket player and we are where our eyes are watching this tiny little ball flash by us really fast. I have to swing or just have the right moment to hit the ball. So this is, or even it could be something trying to predict some a person you're talking to and the consequent actions of what they'll do. This is a scene from Vampire Diaries, a show that was very popular in nowadays. So this is all the data streams that AI should be learning to deal with. We should always keep that in mind when I say learning to predict well. Not like dogs and cats classification or MNIST dataset digital recognition problems. So let me start talking about temporal difference learning. It's a method for learning to predict. It's widely used in reinforcement learning to predict future reward value functions. And it's basically the center, the core of many methods you know about Q learning and SARSA, TD Lambda, deep Q networks, be it even TD Gammon, the world champion backgammon player using deep reinforcement learning from 28 years ago. That was like back in 1992, even before when I was born. And very recently, AlphaGo, it happens not to use TD learning, uses some other kind of reinforcement learning, but it's pretty much reinforcement learning only. The helicopter thing from Stanford videos that you might have seen or heard, they also don't use it either. And then it's okay, it can be used to predict anything. It's a general method after all. But don't be fooled by and reinforce something you read all about TD. It's all about predicting value functions, the reward. But we can use it for literally anything. And since my talk is just about TD, I want to be sure you to think this general use. The initial learning system, even in AlphaGo, was said to have learned from actual outcomes, actual games, and then they would go all the way back to the final outcome. If they were to make a prediction, look at a position, make a prediction, how am I going to win or lose? And they would go ahead and see who actually won the game at the sheer end of the entire 2 hour, 3 hour game. So they would use who actually won instead of a temporal difference learner. So that's what we want to work for. Do we wait and see who actually won, or do we see the outcome on the intermediary state or the return of the end of the entire game, or do we actually do an updated guess from a guess? So let me make that more clear as we go to my next slide, which is about what exactly is TD learning. It's learning to make a prediction from another later prediction. So if AlphaGo was looking at a position to make a prediction, I'm zooming all the ends of the games he won, then it is not TD. It's not learning that prediction from a prediction. On the other hand, if you make a prediction from a position on the move on the board, and then you make one move, and you see your next prediction, and you use that next prediction to form a target, then you are doing TD learning. So the quick phrase is, we are learning a guess from a guess. Sounds a bit dangerous, doesn't it? How would it constrain when it would tie it down? Like if our error was wrong, probably our predictions are way too long. But that is the idea. We want to learn an estimate from an estimate, and we have to talk about that, whether this is good or not. The TD error is the difference between those two predictions that I just spoke about. Two temporarily successive predictions, right? So if you're playing your game, you say, I think I am winning, and then you take another move. And now I think I'm losing. You try to learn from that. You don't know who actually is going to win, not yet. What you try to learn is the temporal difference between your predictions. Now, after that, it's the same as what you are all used to. Just have an error and send it back proper through whatever you're doing. Use any neural network, any algorithm that you're using for the same. It's just really, where does the error come from, or where does the target come from? Let me rephrase it that way. It comes from the end of the game, or does it come from next prediction? So here's the example of TD Gammon originally. It's it's like 1992, and the algorithm had a chess backgammon position, and he would send that into a neural network, which would filter through actually just a single well. Had many versions. The standard version was like a single hidden layer, and he'd end up with this probability of winning. And the error was then probably winning in one position. The probably winning in next position. So we'll look at the change in the estimated probability of winning. that was used as the error. That would be backpropagated through it, and this would learn to just stick it in a corner, playing against itself, learning from itself, from its own trial and error, and it came out to be competitive with the world's best players, really the best in the world. So that's familiar to you now. But what I'm trying to get to is this question: do you need to use TD learning because this all is just to motivate you for that? The motivation is most important to understanding. Here, can I get away with it because you go to the field now, maybe even in the reinforcement lane, you'll find a good fraction of people don't believe in TD learning, and I think they can pretty well get away with it. But it's a real thing we should all be asking: do we really need it? I want you, as people learning about the field, to be able to engage with this question and know the basic facts pertinent to whether we should need to use TD learning or not. And then it's up to you to decide. Here's an example from classic Atari games, very popular in 1990s. 90s kids would remember those. Uh, Beam Rider, Breakout, Kung Fu Master, Space Invaders, Pong, all of that when computers were very native, very naive. Researchers applied deep Q learning to a range of Atari 2600 games implemented in the ALE or the arcade learning environment. Atari 2600 is a challenging RL test bed that presents agents with a high dimensional visual input, about I guess roughly 210 cross 160 RGB video at a frame rate of 60 hertz, and a diverse and interesting set of tasks that were designed to be difficult for human players. The goal is to create a single neural network agent that is able to successfully learn to play as many of the games as possible. The network was not provided with any game specific information or hand designed visual features and was not privy to the internal state of the emulator even. It learned from nothing but the video input, the reward and terminal signals, and the set of possible actions just as a human player would. Furthermore, the network architecture and all hyperparameters used for training were kept constant across all the games. And see how beautifully it has learned. Even to that extent that DeepMind found that it performs all previous approaches on 6 of the games and surpasses even a human expert on 3 of them. I'm gonna come to the questions bit in a very short while. So as you've seen that it's TD learning, but when do we need it, and why do we need it? Well, it's only relevant with multi-step prediction problems. That's the first key thing to remember. Only when the thing predicted is multiple steps into the future. Obviously, if you are predicting the outcome of a game, there's multiple steps in the future. But if you're predicting a label, or like in AlphaGo where the data was the initial data at least, as a guess, then I'll see who won the game, or use that information to then decide who won the game. It's essentially a one-step prediction away. That is not. We want it for multiple steps into the future. So now I want to say that it's really broadly applicable, but you'll be like, Siddharth, you just said that it's only applicable when you have multiple multi-step prediction, but really everything you want to do is gonna be at one point in time multi-step prediction. If you want to predict and see, I have myriad examples to add to that. Let's see. If you want to predict the outcome of a game, a match, or a bet, a gamble, anything of that sort, what do you use? You for prediction learning. If you want to predict what a stock market index will be, everyone these days is going crazy about stock markets. Is this the right time to invest? Will the market go further down or not? Well, really, you could just predict that what it's gonna be, and as you get more data every day and the day after that, you will make like new predictions. You can make some quick money, and then you start liking repeated predictions, and you start falling in love with prediction learning. If you even want to predict who the next prime minister of India would be, you can predict that. Uh, every day as a new event happens, and this lockdown also extends. If you want to predict how long before college reopens, you can do that using prediction learning. Even just yesterday, I was booking my flight tickets. I was literally thinking that when should I book my return. That was also like basis how long corona pandemic is gonna take and how the situations will turn. So that is about it. if you want, like, okay, just a second. Sorry. Um, okay, yeah, the question was, can we treat it as one-step method? Like, sure things happen bit by bit, or do we ignore that and just wait and see what happens? Can you really not learn a one-step model and then compose your entire model from that? And the answer is that we really can't do these things. And I want to try to give some sense of that in the next slide. And I'm really going to talk mainly about this first question. Can we think of the multi-step case as one big step, or do we have to deal with it bit by bit? And the second is, can we learn one-step predictions like a model and then iterate them to get a multi-step prediction when you need to? And I just want to say, I think it's a trap, okay? It's really a trap. This is gonna take this is the longest slide that I have, so it'll take 5-6 minutes. So bear with me on this. This is a lot of text that I've thrown for the first time. I usually try to prefer images or GIFs, but I don't know how I could really properly explain this to you, but I think it is really a trap. I think that it's enough to model the world to make it like a low-level simulation of the world, than to make it think like a tray. It is a Markov decision process, and model the transition probabilities, or treat the world as an engineering model, or where we just learn to predict the velocities and the acceleration, and then effectively on all the accelerations or fractions integrate this low-level differential equation. This is all bullshit, all crap, all trap. These short-term models and then iteration, it feels good because we know that it can be done perfectly on one step, then it can be done perfectly on another, however far we want to look into the future. But there's two problems. First of all, we can't do it perfectly, and when we do it imperfectly with it, because we are always gonna have an approximation, then we try to iterate them. We get a propagation of errors and compounding of errors, and we get a useless long term of prediction. And secondly, of course, it's exponentially complex. uh, why? Because as we look ahead, each step there will be many possibilities. The world is stochastic, and so are our actions. Uh, Maybe have different choices. We might look out for actions, so it becomes computationally intractable. Rather, it will always be computationally intractable. To try to look ahead many small steps into the future. It's like to try to iterate your model of physics to get you how much fun you'll get at Disneyland, or how much fun filled your life will be in corporate or in your masters. There's no future in thinking that way. It's a trap, and lots of people are, in my opinion, falling into it. So, can we not just use one-step supervised learning method and reinforce some? That brings me to my second question, which is, can we not just use familiar one-step supervised learning methods and reinforce something uh, that is currently known as Monte Carlo methods today? I mean, it's just roll it out, cast a die, or flip a coin and see what happens, and use that what happens as a target. So number one, this has costs, and as you're making this prediction, then you're rolling it out to the end. And number two, it becomes super complex, like super compute intensive. It's horribly complex. It's nasty. So you need to remember all the things you did think about yourself. Maybe you are the lion that was trying to make a good chase, trying to predict whether he'll have the ferret for the dinner. Uh, or you have these stuff swirling around you. I've had ferrets running away. You have a glimpse of him. You're feeling of your feet. All of that you sense and you relate to it. So, what is sensible to think, or what would it just be much better if you can do it now, right now? We know all the stuff is in your mind and in your sensors. Can your sensors learn if it's going well or going poorly, and learn now as opposed to wait 5 seconds later when you guys have a whole number or a large number of frames of different sensations and different patterns of sensation? So with a poor temporal distribution, you can avoid these problems with special methods. That is what really TD is all about, specialized methods for the multi-step case. And another reason that you don't want to wait is that sometimes you never know what the target looks like. I don't know, let's say you're playing your chess game and there's a fire alarm, you never finish your game. So you never really see a final outcome. But if you are TD, you may be thought you could thought you were winning, and then you know if it was really a move that you played poorly, or you did something that you can learn from for the next time, until and unless you were checkmated. Maybe the fire alarm was just for like one move away from the check game. So technically the game never ended. But if you were the routine style, you would have not learned anything. But if you follow TD methods, you can learn from each step that you made in the game. So I'm gonna transition to my low level part of the talk here, but I don't want to answer it all out here at this point in time. So I can take some questions if there are any at this point in time. This is just the like first half of my talk. Not sure if I'm audible or was audible. Oops.
Have you got any questions? Yes, you can.
Sorry?
In SQL, we can give those commands.
Okay, okay, at the end. All right. Let's quickly move on to the notation bit in the end then. This is life, how we deal it every day. You have a state that you are currently in, let's say S naught, S0, and at any particular point in state, you make certain actions. Like in currently, you're thinking whether to observe or look at the presentation or not, whether Siddharth is talking bullshit or not. That is your choice, your action to hear the presentation or not. And then you get rewards. The rewards could be whether you took something from the session, or it could be as negative as it was really boring, I couldn't understand one bit that he was trying to mention. So this is how the model of all the model world, or the life as you call it in RL, an agent's life, is based on states, the actions that the agent makes in a particular state, and the rewards that accrue from taking that action in that particular state. And as soon as you've added the reward, you will transition to the next state, that is S1. And these notations that I use here, the subscripts are the time notations. The times are the superscripts. Also, to give a brief idea, I'm using like the random variables as capital letters and the instances as lowercase small letters. So we are eventually interested in the return, right? Which is represented here by G of T, and not R. R is the reward. The capital R that we see here. Return is denoted by G of T. And that is a discounted measure. GD is the return, which is the sum of rewards with the discount most common way of representing it. So we always like weigh all the future rewards with a certain bit of discount. So if you see the first line, the dot over there is a new convention that the statisticians are following today to represent definition. That means it's a pure equality. So G of T is equal to the reward, the expected return that I'm envisaging is the sum of all the future rewards, howsoever discounted that may be. And if you take the gamma out from all the remainder of the coefficients, you can put the brackets in, and you can take one gamma out and reduce one power of all the gammas from the brackets inside. Then you'll try to see that pattern is effectively what G of T plus 1 would look like. If G of T plus 1 would have been substituted in the first equation, it would look very much like RT plus 2 plus discounted times RT plus 3 plus gamma squared times RT plus 4. So you can eventually bring it down to G of T being equal to the expected return being the immediate next reward that you are getting, plus the discounted times what the expected return will be at the next time step. So then what you want to talk about is state value functions, which is nothing but an expectation of the return at a particular state S. So V pi here is the value function, and the pi here denotes the policy here. So the policy is basically a tuple or a list of state action pairs. So imagine any like a policy is with which very easy example is what a government is trying to do, whether to extend this lockdown or not. Or it could be as simple or as naive as if you have climbed the top of the Everest, do you want to dance there, or do you want to be careful when stepping down at the cliffs? So that is what the policy is. So values depends on policies, and the value is basically the expectation of the return, and we just expectation of the return at that particular state. So that's why we've written value of s is equal to expected return, which is g of t, given the state is equal to s. And you just saw g of t derived earlier was r of t plus 1 plus gamma times g of t plus 1 at that particular state. Which if you substitute in the first equation, you'll be able to see, very similarly see that the way the second and third one were derived, it is equal to the policy or the value that you derive at the next state. And then finally, which is if you subtract these two, what you are left is with TD error. That is what we use to back propagate, and that is what we get the learning from, which is the reward at next step plus a discounted estimated value function subtracted with the value function that you have at this particular point in time that you are aware of, because st plus 1 you are not aware of that right now. Let's see that through an example. This is a pretty supervised learning Monte Carlo method, like a very simple one that we've dealt with in college, or any algorithm that we currently use. The backpropagation of the weights or the adjustments happens with the policy, with the value function, and at that particular state, plus alpha is the learning rate or the step size that you want to give, g of t being the target, actual target, minus what is the value that you saw or that you witnessed or that you observed at that particular state. So the tree below represents here, like S of t is basically the first state. The open circles are all states. The filled in circles, the filled in dots are the actions that you take. And after every state and action, there is a reward that you get. And then you eventually land into another state. So what Monte Carlo does is finds the, and obviously these keys that have written in blue color are the terminal states. What Monte Carlo tries to do is find a root mean squared error and get to all the leaf nodes and approximate the error from that and learn from these. On the contrary, let's read the TD method. What TD would do is it would sample which of the nodes I want to pick. It would also bootstrap which of the nodes I want to go into future. And the equation is the same as what we just saw 2 slides back, right? So it is gamma times v of s of t plus 1 minus v of s of t plus the reward that I am getting at that particular state. And then how dynamic programming looks at it is like the expectation of the return, and it would eventually see at it as a whole. So it would look at all the samples, it would not bootstrap, and it would see all possible nodes, all possible trajectories. I'm not saying it's an exhaustive search, it is still far from exhaustive, but that is the it is the expectation of the return that I'm gonna get in all the futures from now. And if you see the coefficient that is changing between these equations is between the Monte Carlo and the TD method is this bit. This this factor, because in Monte Carlo you need human labels, human annotations, and that is a fixed input that you get beforehand. In TD you learn as you go on the fly from estimates, making predictions from predictions. So that is about it. Let's revisit the three on an apples to apples comparison. Uh, Dynamic programming bootstraps, but it does not sample. So the graph looks like fairly on this one on the right hand side. It compares the width or the entire backup. Monte Carlo says, hey, I do not want to bootstrap, but what I'll do is I'll sample a few nodes out. And what bootstrap and sampling means effectively picking out a certain few nodes randomly in between. And what bootstrapping means is effectively getting an expectation right over there. And what TD does is utilizes best of both worlds. It says what I'll do is I'll use bootstrapping as well, and I'll use sampling as well. And that's how you see it's at the opposite end of the exhaustive search. It uses way less compute power, uh, way memory efficient in getting to the states. Okay, let me show you all of this with an example. So it's like Friday evening, and it's like 6 o'clock. We're going back from office, be it college or university, anywhere, uh, and you're thinking that okay, it's 6 o'clock. Tambaram is, let's say, half an hour away from Poteri. It's like 30 minutes drive. I should reach there in just like 30 minutes. uh, but then suddenly the HOD calls you for something and you are stuck there for 5 minutes, and then for 2 minutes, let's say, or there's a long list at line at the queue, so you are delayed another 2 minutes. And then when you get to the parking lot, you're still already 5 minutes late. So you were thinking you are at 6:05 and you have still not started driving. So the predicted time that you think you'll take to go, you'll reach at around 6:35, and hence the total time taken would be 6:40. And why I said 6:35 is because you eventually even saw that okay, it's started raining outside. So imagine it's not like the tech park that we have where we have open, windy windows, but you realize that when you started reaching the lift below in the basement. So you think that okay, it's gonna take me about, let's say, a total of I'll reach about at 6:40 now instead of 6. And what happens is that okay, you start with your car, probably because people in the range would be driving slower, but then eventually it turns out that you have exited the highway, the main highway, in less than 15 minutes, which usually used to take 20 minutes earlier. So that is another difference, huge difference. And as you exit the highway, now comes a huge trailer, huge big fat ass truck over here. So you are now stuck behind this massive truck, and you're not able to overtake it. It's already overtaken you, and it's occupied all the major lane. So now you still feel again that okay, with the truck being in here, I have to rethink why, like, whether I'm gonna make it on time, whether I'll be reaching at 6:30 or not. It's definitely not 6:30 because already 30 minutes have elapsed. And then finally you reach home all huffy puffy, all sweaty, with about like at 43 minutes, 6 past 43, and that's when you reach home. Uh, so what I want to try to convey is here, let's now take this right side table as an example and try to work out how it looks out in both different worlds. What Monte Carlo would suggest is I'll not revise any of my updates unless until I reach the end of my game, unless until I've completed my episode. And the episode here is reaching home. So all the errors here you see would be this long. The first error would be about this, the difference between the actual outcome and the one that was predicted for all these states at different points in time that you were in, at different points of time, thinking in your car. All these are this high, right? And what TD learning, on the other hand, suggests is that after every point in time, I can start making those differences. And that is what the TD difference is. That is what temporal difference error is. And even you'll notice the signs have also reversed. Here it was pretty very positive, and here it's even negative, because you thought initially that you might take 20 minutes, but then it eventually turned out that people were not driving fast enough. The roads were empty because of the rain, and you were able to quickly exit the highway in like 15 minutes. So that is majorly about it. That is the advantages that I want to come to. Monte Carlo and DP is what the cross between them, that is the bootstrapping and sampling, is what makes TD the most effective. It uses lot less memory and is learning from like has less peak computation, because if you see, if all the differentials that you were to make had still that slight bit of an extra edge, how much compute that would require. uh, and obviously it is learning from incomplete sequences. It does not wait for the entire sequence, the entire 643 to have passed and then realize, okay, I am 43 minutes here, so I'm 13 minutes late. I should have thought that when I was taking the turn. That is the advantage of TD. Couple more. So you might also, like, as ML scientists and the research community is always bothered about the one big question: does it converge? Does your method, whatever you're talking about, really converge to a global minima or a global optima, for example? Yes, it does, to be honest. And we'll even look whether it learns faster or whether it learns slower. Let's take another example, which is a random walk. And here on the upper and right hand side, you have a lot of states, A, B, C, D, E, and you have terminal states in the grayed out squares. You have the rewards at each of these state transitions. So you get, when you are state C and you want to go to D, you get a reward of 0, and vice versa. Only when you are at E and you want to go to the right hand side of the terminal state, that is when you get a reward of 1. So for example, like a typical walk could consist of like C0, B0, C, D, E again, and then when you have eventually reached E, you're bound, you do not take a random that goes towards D, you take the one that ends up in the terminal state, which is at 1. Right? So assume that the task is discounted and the true value of each state is the probability of terminating on the right. Initially, what you would think is all the states, let's initialize all of them at a value function of 0.5, for example. So C is at 0.5, D is at 0.5, E is at 0.5, B, and because you haven't at time t equal to 0, you haven't really discovered what your environment looks like, how the states interact with each other, what is the reward that you're getting. So let's arbitrarily set it as 0.5. And for a matter of fact, because C is at the epicenter of this entire state, it's eventually going to be 0.5. What I want you to think though is, what do you think would be the true values of all the states A through E? Give it a moment of thought. It's going to be like 1 in 6 times that you go through these paths will you reach a 1, and the other times you'll end up in a reward which is 0. So the actual return or the actual value that the state A is bearing is 1 by, I've written this in bold because I wanted all of the people to think. So it's A 1 by 6, B 2 by 6, C is 3 by 6, which is 0.5. I already told that. 4 by 6, 5 by 6. And that is what we have plotted here. This is the line that is the true value. So at t equal to 0, you randomly initialize this with 0.5s, and at t equal to 1, let's say you eventually flopped here C to B and B to A, and then A to, let's say, 0 again. That is when you realize, okay, if I go towards left, I do not get any reward. I make no profit out of this. Why should I even go to C? Let me reduce the estimate of going towards A. So what happens is at time t equal to 1, you just learn that, okay, I should not go to A more often if I am in the hunt for a higher reward. At time t, let's say if this graph was, if you continue this random walk, it's completely random normal distribution. You start taking more iterations over and over again. You start realizing that the value of being in state uh, A is getting lower and lower. And as you increase to, like, let's say even 100 iterations, just within 100 iterations of a for loop can get you very close to what the true value is. It will never be, frankly speaking, exactly. So this is the true value. So after 100 iterations, this is what the values your model or your agent has understood or learned, but it's not ever going to be the flat straight line. Let me be honest with you on that, because it is learning from random samplings, very stochastic in nature. uh, However, let's see whether this brings us to the point whether it converges or not. So alpha being the learning rate and the step size parameter, if you put it, let's see it for, okay, Monte Carlo first. So all these curves till here are for Monte Carlo. All these ones that are gray are for TD. So looking at the graph, you can see, okay, it is converging. No, though not at optimal zero, which I've told is it can never be zero exactly. But the values of the error, the root mean squared error averaged over all these states that you were in A, B, C, D, E, happen to be fairly low, 0.25, zero point 0.2, which is a very minimum fraction when you compare it to 100% ratio. And this is the number this is the number of episodes that you need to take when you reach here. So with Monte Carlo, what happens is you take a very fast. It's a quick learner. It's gonna decrease very soon, and that's what happens there. And when you try changing tuning or calibrating these parameters a bit, you turn out that, okay, you cannot do very well better than 0.02, 0.03. That is where the majority of your distribution is going to look like. This is the upper bound, this is the lower bound for that. While when you look at TD, you'll see this lines converges faster and way quicker, and has also a lesser error than what Monte Carlo presented. See the difference at zero point 0.5, or what it would have been at 0.5. Monte Carlo would have given me a 0.1 error, while TD is given me 0.05. That's a massive shoot. That's a massive change that the algorithms need, and that is what saves the computations. Uh, I can also, I think in the interest of time, I should probably skip over some slides, a couple more, but I'll try to make it quick. I just have one more example to present after this. So this is about TD convergence with batch updating, where you put in all the samples together, and instead of, sorry, just give me a moment. You train it on a completely finite amount of data, and it's not super random. It's still random walks, but you, let's say you cap it at here at 25, and you start iterating them over and over again. So the compute updates are according to the TD and Monte Carlo methods are only estimates after each complete pass through the data. So if you'll realize that for a constant alpha or a constant step size learning parameter, under these conditions, MC Monte Carlo also converges, and TD converges faster. This is another instance to prove the convergence. And the final bit, which I want to show is, let's say you are the predictor. You'll be like, okay, this was just a random walk till now. Show us it works on some other example as well. So we can always go and play, build reinforcement learning models around that, but that's going to take a lot of time. Let's try to work out some maths here. Uh, Suppose you have the following 8 episodes where at each state A, you have like the series of every state, being in each state, you get a reward. So after A, you get a reward of 0. After B, you get a reward of 0 again. Then in the next 6 episodes, what you see is you were in B and you always got a reward of 1. And then again, you randomly sampled another episode and then you were in B, you got a reward of 0. So assume that these are totally Markov states. By definition, I guess everyone knows the Markov properties that like you're just dependent on the past regardless of the history, no matter that. And also take let's for simplicity also assume that there's no discounting, no discounting. So gamma is equal to 1 because gamma being point in fractions make things complicated. So assuming that, what do you think is the value of being in state B? It's like 6 in 8 times that you were in B, you eventually got a reward. So is it not 6 by 8? Is it 3 quarters? It is certainly 3 by 4. And then the value of being in state A is what my question is. Uh, there can be multiple answers to that. Well, really, the value depend. So, and this is the state model that might be happening in around your brain. That okay, when I was in B, 75% of the times I used to get a reward of 1, and the remaining 25% of the times I got a reward of 0. But when I was in A, the next state was never a terminal state because you receive always rewards at terminal states, and the reward that I got was 0. So you said that as 0. So can anyone take a guess around what this reward might be? The value of being in a state called A. I think there are multiple answers for that, and that is what I want to present. The value can be thought of as 0. If you were thinking that the value of being at A is 0, then also you are correct. If you thought that the value of being in state A is 0.75, then also you are correct. I'm not saying anything is wrong here. Both of these are correct. If you thought that the value of being in state A is 0, then you are minimizing the mean squared error on the training state, and that is a Monte Carlo method thinking. That is a Monte Carlo style thinking of prediction. If contrarily you want to consider the sequentiality of the problem, you'll end up eventually that okay, every time I'm in A, I eventually landed up in B. That is the only time because you were there, and that is what TD learning methods adapt. They harness the sequentiality of the problem, and they set the value of being in state A as 0.75. So you might be even wondering that okay, if Monte Carlo fits the training data set best and that eventually minimizes the mean squared error, what does TD minimize? I think that is more got to do with a maximum likelihood estimate that I've written. Probably, I don't know it's visible or not, but that is what you guarantee from temporal difference methods. It is the maximum likelihood estimation of being in a Markov model that is generating that data. And this is what is often in the literature, you might hear this being called as certainty equivalence estimate. This is what TD gets. So both of these assumptions were right. So I think I'm coming to the very close of our session. The summary so far is we introduced one-step tabular methods that were model-free in temporal difference. We even saw how bootstrapping and sampling works and how TD utilizes the best of both worlds in which is dynamic programming and Monte Carlos. All of these three are separate chapters in the pioneering book called Reinforcement Learning by Sutton and Barto. We've tried to cover these in a very small duration. Also, always remember that TD methods are computationally congenial. So uh, that is ordered. If the world is really Markov, then TD methods are bound to learn faster than MC methods. That has been there in the industry since long. That is what I would love you to take as a tip. Uh, and though like Monte Carlo methods also have a lower error on past data, but they really are not tapping the sequentiality, or they're not tapping the future rewardedness of the program. Uh, that is majorly about it. Can give you, there's a classic Pac-Man game that reinforcement learning algorithms try to understand. I just want to show you a couple of research avenues that you can think. There's off-policy prediction with linear function approximation. There's non-linear function approximation as well. Finite time theory, whether replay buffers are actually necessary, predicting myriad signals other than reward, as in hold, unreal, or option models. And yeah, so finally, it is learning to predict. That is perhaps the only scalable of learning I prophesize. It is learning specialized for general multi-step predictions, which is, I guess, pretty much uncovering how mind works, how we model the world, how the agents perceive the environment. This is gonna be computationally congenial. It is gonna get you less computational power. You're gonna perform better with your GPUs here. You can even do it with the CPU certain times. And that's what it makes it fast. It makes it data efficient, and yeah, it's just begun to getting used for things other than just reward based problems. So that is about my time. I think we started at 2:10. It's been a great journey with you guys as an audience. Any questions you have? Uh, that is, I am open to that.
Okay, any questions you have, you can ask.
Hello.
Yeah, hi.
And this Murali staff, Siddharth.
Yeah, hi, sir.
Hi. So you said in a multi-step, we are given state action reward.
Yeah.
Every step we are getting some rewards, no?
Yes.
That result is not stable, you know. The result may be winning or losing or something. So given in the example in the chess game, winning or losing. How will you figure out the ultimate result by using this type of rewards?
This guesstimates. Okay. Yeah. So
Yes.
what we actually do is how we also learn as kids by doing actions over and over again. So in one particular bit, let's say you transition from A to B, and then you eventually transition from B. Life doesn't stop there. Life doesn't end there. You just don't stop experimenting. What you do is, okay, that is how even kids learn to stand. They might fall the very first time that they're trying to get up on their knees. It might hurt them. They might think that, okay, I should give away learning. But that is by doing successive iterations of the same thing again and again. So that is why I was talking about earlier the compute that is required. It is so to answer that, your question is gonna be like repeat this for, let's say, 100,000 iterations, and you'll be able to land up that, okay, this is how I'll get a maximized reward. This is how people are investing in trading these days. I think does that answer your question, sir?
I think more number of iterations are required. Am I correct?
Yes, absolutely.
Yes.
So for all the future time states, you have to have all these episodes. You'll have to have at least a couple of 200 episodes to begin with, depending on the complexity of the problem. Yeah.
Good. Another thing is we gave an example starting from Potteri to reaching the Tambram.
Yeah.
So many hurdles we are passing. That is somewhat it is equivalent to learning by the environment, correct? Sequentially, we are taking decisions. Every time we are taking decisions, we are learning the environment, we are reaching the things. This example is somewhat very closely related to reinforcement learning, no?
Yes.
How does it differ from the reinforcement learning, this temporal difference learning?
This is okay. Yeah, a good question. I think we should have I wasn't able to cover that bit, but temporal difference is a kind of reinforcement learning only. It is learning from rewards and punishments. So it is not different. It is exactly the same. It is very well. You put a great analogy there. it is a kind of reinforcement learning only. So all these four Monte Carlo methods, dynamic programming, temporal
yes.
difference learning, which is also called prediction learning. These are 4 chapters in the book titled reinforcement learning.
Okay, Siddharth, thanks.
Yeah, thank you, sir. Thank you
Okay.
for asking. Great. Any other questions?
Yeah, Siddharth, this is
Yeah.
Sridhar sir.
Yeah. Hi.
How are you?
Hello, sir. I'm good. Good. How are you, sir?
Yeah. See, as you said, it is also one of the reinforcement learning.
Yeah.
Uh, Instead of having only learning only the rewards based on the rewards, is it
Mm-hmm.
not good to also take care of the failures? Because in due course, that's what human beings do, no? We also
Yes.
learn through failures. We take stock of the failures, not only the rewards. So
Absolutely.
yeah.
Correct. Very well positioned, sir. I understand your
Thing.
question. So,
Yes, I have not finished it. Something like
uh-huh.
nowadays, people are very familiar with GANs because
Hmm.
I am also researching on GANs.
Yeah. Yeah.
So that will it not help TD?
Yes, 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 absolutely. For the sake of simplicity, I didn't use any of the negative rewards. So I just used zero notation here, which is in the classic book. But absolutely, the rewards can be negative, and when the rewards are negative, that is the punishment, and that is what you want to minimize. You want to maximize the reward at the same time minimize the punishment. So that is the strategy for this global optima convergence, that always maximize the rewards that you're getting while minimizing the punishment that you want to get.
Yeah, the thing is not only punishing,
Yeah,
but in future circumstances, your failures will have a good knowledge about the path. No? So instead of punishing, we can learn that also. That's what.
yes, yes, yes. It's like avoiding the pitfalls.
Ah, ah.
This is the step. Supposedly, this is the by lane I should not have taken in the future. This is
Mhm.
always crowded. That is
Yeah.
kind of a punishment. So that is the by lane that you want to avoid always, and you want to take a particular route which gets you the most favorable things.
Mm.
Agreed. Totally agreed.
And one more thing, see, temporal learning is actually the updates are actually based on the initial conditions. That's what is there. That is another understanding. What do you say about that?
Temporal difference is about learning the error is between every successive state that you go in.
But
So if
yeah, but the initial condition, no, the initial
Mhm.
bias, what you take,
Yeah.
it may be biased towards that. The condition could be wrong, no, initial condition.
Absolutely, absolutely. So, for an example, in this example, we took zero point 0.05
Mm.
here. So, it will take longer to converge.
Mm.
So, for the entire line, if you would have randomly sampled this entire line also, you might have, let's say, zero point 0, like it
Mm.
could have even been a lesser. So, it would have taken a little less longer to reach here.
Yes, yes, yes.
So those are the initial weights, as you taught in the neural networks courses also. Those matter absolutely critically well here as well. Those hold true.
Okay, thank you.
Yeah.
Any other questions? If not, Siddharth, your presentation was very good.
Okay. Thank you, ma'am.
Really, and another thing is, I think you can do a good research and then become a teacher. Okay, so really putting the equations and other things very well. Okay.
Thank you, ma'am. Thank you.